Okay, so welcome everyone to the fourth talk of the season 8 of the Isogeny Club. Today we are lucky enough to have Eda Kırımlı giving a talk. She is a postdoc at the University of Birmingham. And yeah, the floor is yours, Eda. So please take it away.
Thank you so much for inviting me to give a talk here and also organizing such a nice event to you and Maria. So let me share my screen first. So can you see it? Okay, thank you. Okay, today I will talk about refined Humbert invariance and its relation to certain isogeny problems. And here is the outline of my talk. Firstly, I will mention basically about some basics about abelian varieties and quadratic forms. Those are needed to define refined Humbert invariance. And then we will give the definition of refined Humbert invariance and some useful facts about them and give a glimpse of how we can compute them given the polarization. And then we will mention about some applications, potential applications in isogeny-based cryptography. So the first is, of course, abelian varieties. What is an abelian variety? Abelian variety over a field is a connected, complete algebraic group. Abelian varieties are projective varieties, and the group law is commutative. And what is an isogeny? And given a homomorphism between two abelian varieties, a morphism called an isogeny if it is a surjective and it has a finite kernel. And what is a polarization is that polarization is an isogeny from abelian variety to itself, such that it always comes from ample invertible sheaf on A. And the degree of the polarization is defined as its degree as an isogeny. When it has a degree 1, it's called principal polarization. And we are usually interested in abelian varieties with principal polarization, so we can do some arithmetic over them. And abelian variety with a polarization is shortly called principally polarized abelian variety. And then we have two principally polarized abelian varieties, and we want to compute isogeny between them. And we would like the isogeny to respect the principal polarization data. And then a morphism is called, is an isogeny between principal polarized abelian variety if there exists an integer m equal or bigger to 1, such that the morphism dual composition, principal polarization, theta prime composition var phi n times the principal polarization of the first abelian variety. So those are the basic definitions. And for this talk, we are interested in abelian varieties of dimension 2, and shortly they are called abelian surfaces. Although refined Humbert invariance can be defined for any abelian variety, principally polarized abelian variety, but for this specific call and also for the computations, we are restricted to abelian surfaces. And principally polarized abelian surfaces can be divided into two classes. The first class, the majority of the case, is the Jacobian of genus 2 hyperelliptic curves. And the second class is the product of two elliptic curves, E1 times E2. So those are the main object. And in this talk, we are interested on genus 2 curves which lie on a product surface. What I mean by that, we always have A times E1 times E2, which is the product surface shortly, such that we expect the homomodule between elliptic curve E1 and E2, non-trivial, and we get some extra endomorphism from the elliptic curves E1 and E2. And very roughly speaking, the refined Humbert invariant is a positive definite integral quadratic form attached to a principally polarized abelian surface A theta. And it was defined firstly and introduced by Kane in 1994, and then later generalized to any field. First defined for algebraic closed field, then generalized to any fields. And the many geometric features of the principally polarized abelian surfaces can be translated into arithmetic properties of this quadratic form, this invariance. On one hand, we have geometrically very rich object, principally polarized abelian surfaces. On the other hand, we have positive definite integral integral quadratic form, which are arithmetically very rich objects, and to understand question on both sides, we can inter-exchange between them. So what's the quadratic form? I'm pretty sure everyone knows those definitions, but just for the completeness, the quadratic form, we define a computative ring with identity, and quadratic form over n in invariant is just a polynomial, which can be written as xi times xi, and the coefficients come from the ring. And in this solve, we are interested in integral quadratic form, so r is always going to be integers. So very basic example is that an integral binary quadratic form, which is f of xy, and it can be written as ax squared plus bxy plus cy squared, and shortly denoted as abc. And also another case, an ternary quadratic form, it's an integral quadratic form in 3 variable, and it can shortly be written in this way. And in terms of abbreviation, we shortly use ABC, RCT as just the coefficients rather than writing the whole form. So what's representing the number? A quadratic form represents number if there exists a non-trivial integer solution such that f of x is equal to m. And a quadratic form is called positive definite if it only represents positive integers. And in this solve, every integral quadratic form will be, like the majority of time, will be positive definite. Our interest is Refined Humbert invariant. And what about equivalent force? If you take two n-ary quadratic forms over z's, we say that two quadratic form f1 and 2 are equivalent if there exists m in GL and z such that we send the first quadratic form to the second quadratic form f2. And as a very basic thing, we can always represent quadratic form by a symmetric matrix, and that every quadratic form can be written as a 1/2 x transpose A times x, and the matrix A here is called coefficient matrix, and determinant of this matrix is called the determinant of the quadratic form. And in a very similar way, we can define the discriminant. Discriminant is defined by using determinant. If the number of variable n is even, then the discriminant is just determinant times -1 over n over 2. And if the number of variables is odd, then we can define discriminant as determinant times 1/2 -1 to the n -1 over 2. And what's nice about two equivalent integral quadratic form, they have the same discriminant, they represent same integers, even more, they represent same integers primitively. So here comes to the main object of this talk is let's define Humbert invariants. Before defining refined Humbert, which are integral quadratic forms, I would like to introduce other two quadratics, which are closely related to refined Humbert invariants. The first one is intersection form, and intersection form is defined as we take intersection defined by the intersection number of two divisors on an abelian surface, and it defines an indefinite integral quadratic form on the Néron several of the abelian surface, and simply it's written as 1/2 self-intersection of for all divisor in divisor group. And this is an indefinite integral quadratic form in row variables, and row is the Picard number of the abelian variety. And as you can see, there's no polarization or anything involved here. This is just a divisor theory. And another form, which is probably people are more familiar with, is the degree map. Degree map is a positive definite integral quadratic form, such that every isogeny, when we plug into this degree map, it's defined on the home module between E1 and E2, and it gives the all possible isogeny degrees between E1 and E2, and it's integral quadratic, positive definite integral quadratic form in R variables, where R is the rank of the home module. And I mentioned about this quadratic form because in a very specific case, when we have a product surface, let's take abelian surface as E1 times E2, again, no polarization whatsoever. And then we can actually attach those two forms to each other, and it can be the intersection form can be written in terms of the degree map, and it's just the formula is just QA is just intersection form is called the x times y minus the degree form. And then remember that this was an indefinite integral quadratic form in row variable, and this was also the positive definite integral quadratic form in R variable, and so the number of variables are just changed by 2 here. And what about refined Humbert invariance? So let's suppose that we have an abelian surface, and let's choose a principal polarization in this set of principal polarizations. And let's define the following quantity, following quadratic form on the Néron-Severi group itself. So here we define the form as we take a divisor on the Néron-Severi, and we fix a principal polarization already. We take this intersection of any divisor with the principal polarization and take the square root of it, and minus 2 times as intersection number of any divisor there. So when we define this quantity, it's a quadratic form, but in a different way, it has a determinant 0, discriminant 0. And also one nice thing about this quantity is if you plug divisor, also just to maybe mention for those who are not familiar with the language, every principal polarizations come from divisor. So we can do this quantity, we can take the intersection number. And then instead of plugging D, if you plug D plus n times the principal polarization theta here, we will see that by a easy calculation, this is preserved. So this quantity is the same as Q tilde of D. So this suggests that actually we can define this quantity not over Néron-Severi, but over another object, which is called polarized Néron-Severi group. Polarized Néron-Severi group is defined as the Néron-Severi group of the abelian variety quotient out by the Z times the principal polarization we choose. And this quadratic form, let's say another quadratic form on this quotient module, Kani calls it polarized Néron-Severi group. And remember, this quadratic form had a discriminant 0, but when we take this quotient, the new quadratic form we obtain has a very nice structure. It's a positive definite quadratic form, and that is the quadratic form we are interested in. So let's get.
Sorry, if I may, I have a question. Here, Evan, what is the intersection number between a divisor and a polarization? And for the polarization, you take the ample divisor corresponding to this polarization simply?
For our calculations, I will give some formulas. In general, it's defined by like if you are asking for the generic definition of the intersection number, you need to define the cohomologenes stuff. But for our case, specifically intersection numbers, in the case of product surface, they are just some very simple formulas. It's just which comes from isomorphism I will show in a bit. So it's just very basic calculations. So there are formulas already you can plug into.
Okay, but to me, they involve 2 divisors. And here you have like one divisor, like for instance, when you have like D dot theta squared, you have a divisor.
But this D is for every divisor. And principal polarization, every principal polarization is also a divisor with self-intersection number 2.
Okay, so it corresponds.
When you vary over every D, this is a quadratic form, not for one fixed D.
Okay,
Does that answer your question?
Yes, thanks. Sorry for the interruption.
Okay, let's continue to define refined Humbert invariant. A refined Humbert invariant, Q sub A theta of a principal polarized abelian surface is a positive definite integral quadratic form, not over Néron-Severi, but on the polarized Néron-Severi group, and satisfy for every class in this polarized Néron-Severi group that we have this quantity, and it defines us the positive definite integral quadratic form. The self-intersection of every divisor with the principal polarization we fix in the beginning, square it, and minus 2 times of self-intersection numbers of the divisor. So I mentioned 3 different quadratic forms lying over the talk. But as I also shortly mentioned that they are related, they will be related to each other in the computations also. Like we have a neurons, like let's give a dictionary for the notation, maybe for the for following easily. We have one geometric object neuron sever group, and there exists an intersection form, which is an indefinite integral quadratic form defined over this object. And we had defined home module, and there exists a positive integral quadratic form over home module. And we define something called polarized neuron sever group, and refined Humbert invariant is defined over this object. And when A is a product surface, all those are very related to each other. And the number of variables comes from the Picard number or the rank of the home module. For example, if you have a quaternion, if E1 and E2 are supersingular elliptic curves with endomorphism links or quaternion, maximal quaternion order in a quaternion algebra, then we know that this has a rank 4. And we also know that from the Picard number, this in this case, in the supersingular elliptic curve product case, the Picard number is 6. And I already showed you they differ by 2. But in the middle, there is another quadratic form. As you remember, we take the quotient out here, so which reduce one variable here. So in general, like we have 4, 5, and 6, and they are always differ by 1. And you can do the same rather than supersingular elliptic curve. If you take a product surface E1 and E2 is equal to A, and if you choose elliptic curves as TM elliptic curves, then we know that this home module is just a quaternion, just say imaginary order in maximum order in imaginary quadratic form. So if it is a CM elliptic curve, then we can easily see by the calculations that this has a 2 rank, and this quadratic form has 2 variables, and corresponding refined Humbert has 3 variables, ternary quadratic forms, and the intersection form has 4 variables. And stuff like that. This is just for the easy compression. So also there exists a equivalent definition of refined Humbert invariance. Not only equivalent, it also generalized the definition of refined Humbert invariance to any principal polarized abelian variety. For this, first we have to define endomorphism which are fixed by residue involutions. Those are just the endomorphism. Those are just endomorphism which are symmetric with respect to the residue involution. And here, of course, residue involution is defined by the principal polarization of our choice as very minor. It's just the inverse of the polarization composition, the dual of the endomorphism composition of principal polarization. And we just take all the endomorphisms which are fixed by residue involution here. So if we define this set, we can see that actually the neuron sever group is isomorphic to this set, the endomorphism fixed by residue involution set. And then we can define Humbert invariance in a different way. We take an endomorphism rather than taking a divisor. We take an endomorphism fixed by residue involution, and we define the following quantity. The refined Humbert invariant can be written as trace of the nu square minus 1/4 trace of nu square. So that's the another definition of refined Humbert invariance, and this can be extended to any dimension rather than only dimension 2. So yeah. So for our case of interest, why I can't. So yeah, and let's recall a theorem from Kani. And as usual, we always fix A is equal to E1 times E2, product of 2 elliptic curves, because we're interested on the genus 2 curves line over this surface. And in this specific case, the nice thing about it, we have a very nice group isomorphisms, which is from group isomorphism from this object to neuron sever group. So we have a group isomerism between Z's direct sum, Z direct sum homomodule between E1 and E2 to Néron-Savary group. And you just take two integers and one isogeny. And by using two integer and one isogeny, you can create a divisor, which is given by this in the definition. And this is a divisor in the Néron-Savary group. And here is just A minus 1 times the principal polarization of the first elliptic curve and the B minus degree of the isogeny times theta 2 plus the graph of the isogeny. This is also divisor, which is just defined as x minus v of x. Maybe I should have wrote that. Yeah. So this has very nice interpretation in terms of divisors. Instead of writing in a complicated way, we can represent divisors just by two integer and one isogeny in this specific case. And moreover, by using this interpretation, we can compute the intersection numbers in an easier way as well. The intersection of, let's take two divisor, D1, I can write that as a B and some isogeny, varphi, and I can take another divisor, D2, which can be written as A prime, B prime, and varphi prime in the Néron-Savary group. And intersection number of these two divisors is just given by this formula. And A times, it's just a multiplication of two integers, multiplication of two integer, and this is the bilinear form attached to the degree map, and the definition is the bilinear form associated to the degree map, and it can be written in this way. So this quantity, in this specific case, because of this nice isomorphism, this intersection number can be computed in an easier way. And that's the case we are interested in. And I think we already mentioned shortly, but as we know that we can represent the divisor in a different way, the next question is how we can see that like a divisor actually gives us a principal polarization. Can I give a criterion for that in 2016? And let's again take A is equal to E1 times E2, and P of A is the set of principal polarization. And we know that we can represent principal polarization for this surface as D, A, B, and H, or H some isogeny. And then we can see that this divisor is a principal polarization if and only if this A is equal to A is bigger than 0, and A times B minus degree of the isogeny H is 1. So also every principal polarization also can be written in this way. So as I mentioned, like this gives us this group isomorphism gives us a nice way to write divisors. It's two integers and one isogeny, and it also allows us to compute intersection number in an easier way. So again, if we repeat the setup, we are interested on this surface, which is just a product surface without polarization. And we would like to understand curve of genus 2 which lie on this product surface. And this product surface can be CM elliptic curve, E1 and E2, or we can choose E1 and E2 supersingular elliptic curves. And depending on the corresponding refined Humbert invariant will have a different number of variables. So for example, if you take a product of the elliptic curves such that an homomorphism ring of the elliptic curves is just a quadratic order image in an imaginary quadratic field for some non-square D, then the corresponding refined Humbert invariant, so such as after choosing a principal polarization, is corresponding refined Humbert invariant to such a curve as CM per product surface is a ternary quadratic form. If we choose product surface A, E1 times E2, such that an homomorphism ring of the elliptic curves are a maximal order in a quaternion algebra from phi to P and infinity, and by the calculations, number of variables formulas I gave you, we can see that we find Humbert invariant attached to such a curve on the product surface is the quintic integral quadratic form. the reason I use quintic here, in the literature, people usually use quinary, but I'm following Kani's Kani's terminology. He calls them quintic, so this talk is going to be quintic. Yeah. And the next definition is that about the type of the polarization. A polarization is called reducible if it comes from the class of some elliptic curves, E1 and E2 on the abelian surface. Otherwise, it's called reducible polarization. When the principal polarization is a reducible polarization, we know that it comes from, that divisor is comes from actually a smooth curve of genus 2, such that the principal polarized abelian surface is isomorphic to Jacobian of genus 2 curve with a theta divisor, such that theta is actually in the class of T. And for this irreducible polarization case, can you use as a notation Q sub C for the refined Humbert invariants rather than writing Q sub Jacobian of C with theta divisor for easiness of the notation? So why I mentioned about this, we have something called the irreducibility criteria. We can actually see that if the corresponding, if we choose a polarization by using refined Humbert invariants, we can understand the type of that polarization, whether it's a reducible or irreducible. So, for example, this is called the reducibility criterion. And if again, we are in the same setting, and if the theta, the polarization is irreducible, if and only if the corresponding refined Humbert invariant of this principal polarized abelian surface doesn't represent 1. So this gives us refined invariants gives us a very nice way to actually check the type of the principal polarization. And again, everything is here done by the polarization calculation. You just need to fix the polarization and compute the corresponding refined invariant by some formulas. And then you can just check if it represents 1 or not, which is a very quick test. And you can see that the polarization you choose is actually reducible, which is product polarization people call in isogeny community model, or irreducible polarization, which comes from genus 2 curves. And one nice thing, another useful thing about defined Humbert invariants in dimension 2 is just we can understand elliptic subcovers, and we can understand the split algebraics from Jacobian to product of 2 elliptic curves. Let's first define elliptic subcover. An elliptic subcover of a genus 2 curve, or any genus G curve, is defined as a finite morphism from C to an elliptic curve and not factoring over a non-trivial algebraic of E. And what's nice about refined Humbert invariants, we can actually understand all elliptic subcovers if we have the corresponding refined Humbert invariants. And we say the next term is the Kani, and a curve C over K has an elliptic subcover of degree n, if and only if its corresponding refined Humbert invariant primitively represent n square. And in a more accessible way, I guess, for isogeny community, this means that there exists an isogeny from Jacobian to some product of 2 elliptic curves, if and only if the corresponding refined Humbert invariants of this curve or Jacobian primitively represent n square. So one more thing also, which is we can understand by using refined Humbert, is the automorphism groups. Let's first give let's take a finite group, and we take the EG is defined as the number of involution in this group. And for any integer n, we can define this RnQC quantity. This is actually the number of representations of n by QC. And in our setting, we can write these sets as all the divisor in the neuron subary of this Jacobian with the theta divisor, such that when we plug the class of the divisor, it represents n. And we have access to that. There is a very nice theorem about understanding the automorphism groups. If we have a genus 2 curve over K, then if we compute the corresponding refined Humbert invariance, we can actually see the automorphism group. It's just the number of representation of 4 by the quadratic form QC, which is a refined Humbert invariant, is actually coordinate of the number of involutions of the automorphism group of genus 2 curve minus 1. And moreover, if the number of representation of 4 is bigger than 0, then we can say that there exists an isogeny for some elliptic curves from Jacobian to E1 times E2. If it is the number of representation of 4 by QC is bigger or equal to 3, then we can even see that those two elliptic curves are isogenies in the product to each other. So, yeah. And in our case of interest, we are trying to understand some isogeny problems in isogeny-based cryptography. And we would like to understand some product of the elliptic curves, and we want the endomorphism ring structure on elliptic curves as a maximal quaternion order in a quaternion algebra. And in this case, as I already mentioned, the corresponding refined Humbert invariant has 5 variables. And the next question is how we can compute this quintic refined or quinary refined Humbert invariants. And for this, we have some nice and useful formulas for the determinants of the neuron severity and all other stuff. And maybe before going any further, I would like to emphasize that the calculations have been done in this talk. It's always start with the principal polarization. So if you ask me, if you give me like another model of the genus 2 curves or Jacobian or elliptic curves, there's no direct algorithm yet that you can start with the curve and compute refined Humbert invariant directly. So all the computations are here, are done when we are given a principal polarization, and then we can compute the refined Humbert invariance. The question of how we can compute the refined invariance given the model of the curves, it's like mostly open for the quintic case. Or another question is when we are given a random positive definite integral quadratic form, can we check that it's actually a refined Humbert invariant coming from a principally polarized abelian surface? This question is also a very hard question, but at least there are some partial results. I didn't mention here, but if the refined Humbert invariance is a binary quadratic form, which means it's a product of two elliptic curve with trivial endomorphism rings are just set. And if that represents a square, then this has been done by Kani. And also for the ternary quadratic form, Harun gave a algorithm recently, I think on like a month, 2 months ago, that you can actually, the classification of the ternary quadratic form for a CM product surface has been done by Harun in his PhD thesis. And by using this classification, so you just pick a random ternary quadratic form and check the conditions he gave, and you can actually see that that is actually refined Humbert invariance. And the next question, starting from refined Humbert invariance, in this case, is a ternary quadratic form, how we can compute the genus 2 curve or any other model. So this has been done recently by Harun Kır, who is in the audience right now. But we don't have any algorithm to do either starting from curve and compute the refined Humbert invariance, or starting from the quintic refined invariance to get something about the curve structure. So for quintic case, this is mostly open. So all the algorithm I give you is mostly you have some access to principal polarization, and you compute all the intersection formula, you make a symbolic computation and compute all those quadratic forms and check the generic stuff. So in terms of determinate conditions, we already mentioned that degree map defined on module. and the intersection form was related by a formula. And then this also reflects on their determinant formulas. So we can always, once we have access to this determinant, we can compute this thing. And in the computation, we have to check first such things. And one another useful theorem we can use is that Duetticani again. And if genus 2 elliptic curve has an genus 2 curve has an elliptic subcover such that characteristic doesn't divide the degree of this subcover, that should have been capital. Sorry for the typo. And if the Picard number of the rank of the Néron-Severi of the Jacobian of genus 2 curve is bigger than 3, and if the determinant of the refined Humbert invariant quotient out by 2 to the 2 Picard number minus 3 is square free, then we actually directly can say that this is a Jacobian isomorphic the product of two elliptic curves. And another useful theorem we use is if we have a presentation of the genus 2 curve such that E is an elliptic curve, E prime is an elliptic curve, and this is something called isogeny defect. And we want this degree n, which means the subcovers have degree n. And if characteristic doesn't divide n, and then if the rank of the home module is bigger than 1, then the corresponding refined Humbert invariant is a positively quadratic form, and it has to satisfy all those conditions. And like it has to satisfy some determinate condition with respect to home module, the quadratic form over home module, and it has to primitively represent n squared for n here. And the third condition is even more general. This is the necessary condition for refined Humbert invariance. It always, up to modular form, it always has to represent 0 and 1. And since this is the genus 2 curves, we have a Jacobian, and this means that the corresponding polarization is a reducible polarization, and this quadratic form cannot represent Y for all x1, x, r1, and z. And one more theorem from Kani is that if the presentation of degree n of the genus 2 curve E prime and isogeny defect phi such that it doesn't present, then the isogeny defect is 1 if and only if it is isomorphic to product of two elliptic curves. So those theorems are used in the computation for sanity checks, and you don't land in somewhere which is wrong. So how we can use these theorems is the next thing. The applications in isogeny-based cryptography. And here we are going to mention about 3 applications. The first application is a security reduction between computational refined Humbert invariant and isogeny problem in dimension 1. So in the context of C-side and C-side, I will explain that in a bit. So this is an application in dimension 1 case. So you start with some invariants attached to abelian surface in dimension 2, and you get actually some reduction to isogeny problem in dimension 1 for super singular elliptic curves. And second is we can understand isogeny degrees of dimension 1 between any pair of 2 super singular elliptic curves. And the next one is we can test the Folkler. This is an application in dimension 2, different than the first 2 applications. We can test the distribution of product of elliptic curves in the full isogeny graph. We can test the detection of NN splittings in the isogeny graph, and we can check the minimum walks to split surfaces. So let's first briefly mention about security reduction. With my PhD advisor, Chloe Martin Day, we proved that the computing the quintic refined Humbert invariant of E times E prime, where E and E prime are supersingular elliptic curves, is computationally equivalent up to polynomial time algorithms to solving the isogeny problem between E and E prime. And that is the CQ-sign case. So we can do that in the C-side case too. In the C-side case, we have a elliptic curves, and their endomorphism rings are quadratic orders. So the corresponding refined Humbert invariants are ternary refined Humbert, ternary quadratic forms, positive definite ternary quadratic forms. And the computing, if we start with the C-side setting, we take a product of two elliptic curves such that the endomorphism rings of those two elliptic curves are just quadratic order in an imaginary quadratic field. Then computing the ternary refined Humbert invariant of E times prime is computationally equivalent to up to polynomial time algorithm to solving the isogeny C-side isogeny problem between E and E prime. So those are the two things we proved in our paper. And so that's the security reduction. So first application. So for the second application, how we can analyze the isogeny degrees between any random two supersingular elliptic curves. For this, first I have to mention about the lemma duodecany again. And if you take two elliptic curves over a field, and as usual, we take a product of two elliptic curves, and we choose a product polarization on each product polarization. And in this specific case, if we choose a product polarization, there exists a formula we can write to find Humbert invariants in terms of degree map. So for AB in Z and for the isogeny in Hom E1, E2, we can write the corresponding refined Humbert invariants of E1 times E2 with the product polarization is just a square plus 4 times degree map. So any product of two elliptic curve with product polarization can be written as x squared plus 4 times degree map on the Hom module of E1 and E2. So how we can use this information to understand some questions. So first, we need to complete the refined Humbert invariants and given the polarization again. And this has been done in collaboration with Garush Korpal. I believe he's in the audience also, in our paper called Refined Humbert invariants in supersingular isogeny degree analysis. So the setup is the same as usual. We have A is equal to E times C, product surface for a supersingular curve E, which is a maximal quaternion order in a quaternion algebra. And we know that corresponding refined Humbert invariant is the quintic integral quadratic form. And in this specific application, because I want to understand isogenies in dimension 1, and I want to use the lemma, which is I just showed you in the previous slide, which relates to refined Humbert invariant to x squared plus 4 times degree map. We just have to choose the polarization in a product polarization, meaning it's reducible principal polarization in another notation. And so we list all reducible principal polarization which can appear over a fixed field. First, you choose the product surface. As there is only one up to isomorphism as an unpolarized abelian surface, you can choose any elliptic curve of your choice. You can choose any maximal order, depending on your choice. And you just list the principal polarization and reducible ones. You can write a brute force algorithm or random polarization algorithm such that you sample all the reducible principal polarization. And we calculate refined Humbert invariance. So is again how we want to understand the following quantity. So I want to understand all the degree maps over a fixed field. So those are the degree maps I want to see. And these E1 and E2 elliptic curves, they are ranging. So those are every different pairs of elliptic supersingular elliptic curves defined over a p square. And I want to see the minimum number represented by degree forms. And I want to take the maximum of all those minimums to see that what is the expected max mean, what is the maximum minimum degree which can appear over a fields. And again, we don't use any isogeny computation here. We don't use anything. We just use the polarization and this refined Humbert invariance and some theory over there. So we don't actually compute any isogeny in this talk for anything, even though we want to understand some isogeny problems. It's just all the things are coming from some divisor intersection formulas and quadratic form calculations. So how we can do that, as I told you, we sample or give an algorithm for all polarization or only reducible ones is enough for this specific understanding of this value. And we compute the refined Humbert invariance, and we use the lemma for the reducible principal polarization. I can write refined Humbert invariance as x squared plus 4 times degree map. Then we pull out the degree maps from refined Humbert invariance, and then meaning that we have all those degree maps which can appear over these fields for every possible home module. And then we list the minimum values represented by all the forms here. And again, of course, we have the number of, like this number has to be always smaller than number of reducible polarization, which is given by H, which is a class number given by Ehler. And so you can actually check that you're in the right spirit. So we calculate all the quadratic form which come from all the refined Humbert invariance for the reducible polarizations. And then we compute the minimum of each quadratic form here. And we have this set of minimum of all those quadratic forms, and we take the maximum of it. And these experiments align with the formula, which I didn't write here in this Keysign paper also. So they give a asymptotic formula for that, and we can actually check that our experiments align with their formula. And their formula is just depending on some lattice reduction and some depending on 2 pi's. I forgot the formula. So one example to see. Let's take a product of your favorite supersingular elliptic curve, and we choose principal polarizations. For the computation in our paper with Garush-Korpal, we choose specifically prime p congruent to 11 modulo 12, and we choose this specific maximal order in a quaternion algebra ramified at p and infinity. You can basically choose any maximal order, but the only difference is that when you plug all the formulas, which is very ugly and very long formula, which I couldn't fit into slides, and then they have to, even if you make one mistake, then the quadratic forms are not going to have determinacy, and you can pull out the refined Humbert invariance. So this just, when you fix one, you have to be very careful about the symbolic computation so that everything is actually respecting this quadratic form. Again, you can choose any other maximal order in the quaternion algebra, and the result you are going to get is going to be the same for the same prime. It's just the computations and the quadratic forms you are dealing with will be in another basis. So what we did, we sampled so many principal polarizations, which is 63,050. And among them, we choose the ones only representing 1, and only 2,939 of them represent 1. And among these 2,939 quadratic form, up to isomorphism, up to isometry, we have only 39 of them. One of them is an example here. If we choose this principal polarization, and the diagonal is 12, 40, and the non-diagonal element is just a isogeny representing between two elliptic curve. And here, these beta 1, beta 2, and beta 3 are the basis elements here. Just for the shortness, I wrote beta, but they are coming from those basis elements of the quaternion, maximum quaternion order. And again, this is if you write a random algorithm to sample a principal polarization, you're not going to have something nice as this. The coefficients are very huge if you have a randomized. But if you have an algorithm to do that kind of brute force way, in a naive way, you can actually have, you would need to use a high performance computer, which is what we did in our paper with Garush. And then you can have relatively nicer and smaller coefficients for the principal polarizations. And you plug this principal polarization to the symbolic computation you already have. And that's going to give you the refined Humbert invariance. And we always take everything in LLL reduced form. So that's why that's a just nice looking quadratic form. Otherwise, it's very big coefficients again. And then, as you can see, that these represent 1 because the first coefficient is 1. And by using the lemma, we can pull out the degree map from rest of the quadratic form. It's just 4 times the degree map. And you can write the degree map quite easily as this form for this specific example. So this is just the computation of this one of them. What we did, we sample all the principal polarizations, we choose the reducible ones, and we compute all the refined Humbert invariants, and we plug out all the degree maps, and we check the minimum of all those degree maps and take the maximum of it. So it was a lot of computations. So that's the data from prime 11 to 419. This is the data where we sampled our form with the randomized principal polarization algorithm. We basically sampled p cube of them because roughly we have p cube of principal polarization. And this is the number of all principal polarization. This is the number of reducible polarization, product polarizations. And those are all the principal polarizations. And we compute the refined Humbert invariance, and we only keep the ones representing 1, which is this column. And then we take pairwise isometric tests between those quadratic forms. And as you can see, those, for example, in the first example, 546 of them only gave us 3 different up to isometry, the lattice, or up to equivalence in terms of quadratic forms. And this quantity is something else, which allows us to check that we found it is the genus of this specific quadratic form, Q5, which I didn't define. And if we check this genus calculation and we keep the ones representing 1, we can actually check that that's the only way that we can check that we obtain all the refined Humbert invariants. Because one important thing about refined Humbert invariants, you can have completely different principally polarized abelian surfaces, but their corresponding refined Humbert can be the same. So this H is never the exact, we never get to this exact number, but the number of polarization, this is the upper bound on the number of refined Humbert invariants with reducible polarization you can get, because this is the number of reducible polarizations, and you do all those. When the prime gets bigger, you see that those are always smaller. So you always have less than equal to number of reducible polarization. And we computed this maximum of minimum between all those degree maps we plug out from refined Humbert invariants, and those are the numbers. And we check this data with the skew sign bound, and it aligns with the bound. Yes. How much time? Oh my God. Sorry, I'll be quick. The next example will be in dimension 2. How we can take folklore, split surface, and minimum box. The setup is the same. We have this symbolic computation for P, congruent to 11 modulo 12, and the same quadratic form. Differently from the previous application, we choose reducible principal polarization so that we can stay on the Jacobian of genus 2 curves. And by using the splitting theorem dueticani, we can actually check that there exists an isogeny from Jacobian the product of elliptic curves if the corresponding refined Humbert invariants primitively represent n square, and primitively is very important here. So given a reducible polarization, we compute the refined Humbert invariants. We design an algorithm for primitively checking n squares. If it primitively represented, then we say that there exists this splitting isogeny from Jacobian the sum product of elliptic curves. And we did that in our paper for n is 2 to the k, so that we can say in the Richelieu isogeny graph, and we can check some already existing experiments with Ben Smith and Enning Floyd in their 2 papers. And very quick example, as I am running out of time, very quick example for a very small prime. If you take P 165, we just check splitting of 2 to the k isogenies, and we compute random irreducible polarizations, and then we compute the refined Humbert invariants, and we check the primitive solutions for 2 to the k's, and k is between range 1 and 31 here. And since this is a relatively small isogeny graph, you can see that, for example, this type 1 surface, this 1 means just numbering, is the first surface has always a splitting for each key in this range. For second surface, there is no, in neighborhood, there is no product of 2 elliptic curves. And the same goes like that. And all those primitive solutions for first surface, there exists for every k. For the second surface, 1 k is missed. And for example, fifth surface, we have 2 cases missed, and so on. And you can do this experiments for relatively bigger primes because the random polarization algorithm is quite sufficient. You just have to sample as many as possible to see some patterns. And another thing you can do for a bigger prime is testing this distribution of the product of elliptic curves in the full isogeny graph. For one example, for P 1103, we sample 1000 random principal polarization, and by irreducibility criteria, we check which ones are the irreducible polarizations, and out of 1990 were irreducible. And we computed the corresponding refined Humbert invariants, and they were all distinct, just by luck, because the algorithm is very randomized. The corresponding refined Humbert invariants are like that also. So I picked 10% of all those things, just pick 107 of these invariants, which means there exists at least 107 superspecial Jacobian vertices in the full isogeny graph. And then we know that the corresponding Richelieu isogeny has a diameter 8 in this case. And we can check all those primitive representation of 2 to the k for all the data we have. And we can see that only minimum 2 surface is 1 step away from product surface. And 27 of them minimum surface is 2 steps away from product of 2 elliptic curves, and 60 of them are 3 steps away from product of two elliptic curves, and 18 of them are just 4 steps away from product of two elliptic curves for this specific prime, and for all the 99 surface we checked. And again, I don't know which surfaces they are, but I know they are somewhere in the isogeny graph and they are distinct. Those are the things we check, but I don't know what genus 2 curve it is, and I don't know anything about the equations of these genus 2 curves or Gauss invariants or anything like that. It's just everything is done by quadratic form and polarizations in this kind of experiments. And we also checked for the random walk. This is a bound given by Enric, Florit, and Ben Smith for the random. If you take a random walk, it has to be bigger than that to make it as random as possible. We also checked this data for this range between k is 10,000 and 8 is this is the minimum random bound in the Richard isogeny graph you can get, and 65 of the refined Humbert invariants were highly primitively represented by 4 to the k, but 42 of them failed even in the primitive representativity in as a local conditions. So those kind of different experiments we made for different primes and sampling as many as possible quadratic forms. I guess and this last slide is we can check the automorphism group of the genus 2 curves. Again, check the just select the irreducible polarization. We know that it's corresponds to some Jacobian, and we have a formula given by the number of representation of form, which gives us automorphism information about the genus 2 curves. And this is the data we compare with the Ibiokima, Katsura, and Oort bounds because they already computed for. And this first stuff is their count. The second counts in the tuples are our counts. And this is supposed to be always smaller because two refined Humbert invariants can collapse the same surfaces. And yeah, so that's the data for automorphisms for first 20 primes. Yes. And thanks for listening. I'm so sorry I ran out of time.
Thank you very much for the presentation. And yeah, don't worry about the time at all. Pretty close to the 1 hour mark, so really not that bad. And yeah, as usual, if people have questions, please unmute and ask or type the questions in the chat. So maybe I can. Oh, okay. Well,
I have one, but I can wait, Jonathan.
no, it's okay. I was just gonna ask. I think you mentioned, you probably mentioned it, and I was just I just missed it. So could you remind me what was the significance of the forms representing one? Why were you or like why were you only interested in those?
Because in that case, if it represents one, the corresponding principal polarized abelian surface is the product of two elliptic curves with product polarizations. And for the second acceleration, and you can actually plug out the degree map on the home module, and you can understand degrees of elliptic curves between dimension 1 supersingular elliptic curves. So you started something in dimension 2 just by polarization, and you understand all the degrees which can appear between two random supersingular elliptic curves in dimension 1.
Okay.
Yeah.
Yeah, sorry, it was probably basic question. Thanks.
Yeah, can I go?
Yes.
So thank you, Eda, for your talk. I really liked it. In your first application, you had some table where you had this D, which is the maximum of the minimum. Am I saying it right?
Yeah, I think it's second application. Yeah.
Yeah, right. If you can put the I think it was there, maybe. Yeah.
This one, I guess. D.
There you go.
It's
Yeah.
quantity. That's the quantity. Should have
So
written here.
this looks a lot like a diameter, but it's not a diameter, right?
No, it's not. Because because this is a dimension 1 case, right? So you start with dimension 2 object, and so we have the refined Humbert invariance of the product surface with product polarization. And in this case, it gives us a compute the degree map on home module. So this home module, the degree form, if you plug the isogenies, it will give you all the possible isogeny degrees between E1 and E2. So here, we just randomly choose reducible product polarizations, and we compute the refined Humbert invariance, and we use this formula, which is just x squared plus 4 times, you can write x as this x squared plus 4 times degree map. So from dimension 2 object, you switch to dimension 1 object, and you can understand if you list all the reducible polarization, and if you compute all the refined invariants, you can find all degree maps which can appear on any home module between this specific finite field you started with. So those are going to be different E1s and E2s for each reducible polarization. And they can collapse sometimes, but like you will see all the possible ones. So this is dimension 1 application. So it's not like diameter much, actually. But there's a sticky sign HT paper. They give a bound on the maximum minimum degree which can happen, which is important for the design of the sticky sign signature. So that was the motivation behind computing this in the first place, actually. So to see that if their bounds match with us and stuff like that. Actually, when I did this, I think there wasn't even that bound. But by the time I made this paper public, so they hit the bound public also in a published version. So yeah.
I see. Thank you.
Maybe one thing, Enric, in the dimension 2, which I didn't have time to mention, your paper with Ben Smith, we can verify all the data with this invariance. The only difference is we don't compute the Gus invariance and all those isogeny computations. We do everything on the quadratic form size. So in my thesis and in the draft of the paper, which is not public yet, I compare the data with your data so that they align, like all the automorphism informations, all the random walks, like these diameters, like they all align. You can see them without actually computing any Gus invariance and any chain of isogenies. So that was the advantage is you don't have it. You want to understand something about the isogeny problem, but you don't compute an isogeny at all. So everything is on the quadratic form and their calculations and stuff like that. But one downside is you don't know where you are in the isogeny graph, but you can check they exist and they can happen without actually where it is. So anything done randomly can be checked by these invariants.
Cool. And related to that, can you then check any diameter? Say you want to compute L to the k isogenies with L different than 2? You can do that.
But diameter is just... Yes, but like the diameter definition is quite different because those invariants just give me like the isogenies between... It's actually more useful for the Cosell and Smith algorithm to find from Jacobian to product surface isogenies. So between two Jacobians, they don't necessarily say anything. I mean, they say some information, but I didn't mention here. It's just like, in my computations, I can say, with all your like diameters, there was always, in the computations experiments I made, there was always an isogeny to split surface smaller than the diameter, and which is mostly way smaller even. I mean, this is for visual isogeny graph, for example. Yeah.
Right. I'll take a look. Yeah.
Okay, thank you. If there are no more questions, then let's thank Eda again. Thank you, Eda. And in 2 weeks, there will be Ryan Rüger giving us a presentation. So yeah, see you all then.
Thank you.